Our next question here is from the initial value problem, 6x times the derivative of y with respect to x plus y is equal to 0. Y of -1 is 1, and we want to apply Euler's method where step size h is equal to 0.15 to approximate the solution on the interval from -1 to 0.5 inclusive. Because of the way that our equation here is, to do this in Matlab, we would need to express this differential equation as the derivative of y with respect to x would be equal to -y divided by 6x. The interval of -1 to 0.5 inclusive just be -1 and 0.5 in brackets. This uses an h of 0.15, which means we would need to solve that 0.5 plus 1 divided by 10 would give us the value of 0.15, which means we need to use a value of n as 10. And additionally, we see from our initial condition that y of -1 has to be equal to 1. The function that we are going to use in Matlab is going to be the following. Euler 1. And then in parentheses, we're going to have a -1 and 0.5. In brackets, no comma or anything. 1 and 10. In order for that to then map to exactly the way that we need that inside of Matlab. So let me share then my Matlab screen. Being this, we have our equation, our formula, the coding for it here in Matlab. And we need to make sure that our function is inside of here. That would have to be at line number 24 here on the bottom. We have z is equal to -y divided by 6 times t. It uses t instead of x, but it's the same exact thing. So z is equal to -y divided by 6 times t. And that z would then correspond to that derivative of y with respect to x. That would be our function. And that would have to be in there in order for us to get this answer. All right. So the command that we write, exactly what I had on the page. This would be Euler 1. And then in parentheses, we have our interval. So that was -1 space 0.5. We're going to close the bracket. And that'll be 1 and 10 with those commas. And watching that on here, we get our various values of y and our various values for x in this particular case. As you can see, it does indeed do it all those times. So we have each of those values and then the corresponding solutions here as the y value. And we can also see we also are given a plot of this as well, but we don't particularly need that for this particular question. We just care about these. So let me just write out that table of solutions to help aid us in what we are doing. So let me make note of these values of x very quickly. This went from -1, -0.85, -0.7, -0.55, -0.4, -0.25, -0.1, 0.05, 0.2, 0.35, and then 0.5. The value of t, which will just indicate our step size of 0.15, is going to be the same for all these values. So I won't bore you to tears with me writing all this physically out. And then we have our values of y. So for an x of -1, that was 1. For -0.85, that was 1.025. For -0.7, that was 1.0551. For -0.55, that was 1.0928. For -0.4, that was 1.1425. For negative 0.25, that was 1.2139. For negative 0.1, that was 1.3353. For 0.05, that was 1.6691. For 0.2, that was 0.8346. For 0.35, that was 0.77. Excuse me, 0.73, that is, not a 7. 0.7302. And then for 0.5, that was 0.6781, which corresponded to that MATLAB output. Let me know if you have any questions or concerns. Thank you.